So we are approaching interesting things. I will today talk about the transfer principle. So let me remind you that we have a standard universe U. So standard universe is based on some base set S, and then we consider subsets of S, subsets of set of subsets of S, set of subsets, and so on. So we have the hierarchy of different entities, different objects, and we, as I explained more than once, this hierarchy contains all the necessary mathematical objects which we need for our mathematics. We have its counterpart, non-standard universe. To have this non-standard universe, we need to have I index set and F ultrafilter. And I. So these are the necessary things. So elements of this universe are constructed, and this universe is also a hierarchy of sets, but here we have some basic set, and then we have some of its subsets. It's the next floor. Next level will be some subsets of the previous floor, and so on, not all. So this is called non-standard universe. As I know, I will repeat when necessary more detail. Now suppose we have element, say, A in U. So A is a standard element in standard universe. And I put in correspondence to this A some element A star in U star, which is and such yes, so this map is also denoted by star. So star map, which makes of a standard element, makes a non-standard element. So it is defined as follows. If you have element A in S0, so it is not set just individual element, then we consider the function f of I equals A for all I in our index set. And we consider the set MF, set of all G, such that G of I equals F of I for almost all I. Almost all means the set of I where it holds is belongs to our ultrafilter. So this this MF is by definition is by definition this MF. So essentially it has as much content as has element A. That is called A is no, okay, I will tell it later. Now suppose that our element is a set. This means that if A belongs to S check minus S0, so it is a set, then we define the following thing. Consider the set A equals the set of G of I, such that G of I elements of A for almost all I. Yeah? So this is a particular case of the elements of our particular case of elements of our non-standard universe. So this particularity is that condition of G of I, in fact, does not depend on I. For all I should be element of for almost all I. Yeah. So this is a definition of A star. And so in all cases, elements of the form A star are called standard elements of star U. Yes. So they are themselves sets. These elements and can be quite complicated, but they are the closest to the standard elements, to the standard universe. And now for the standard elements, we have the following things which I have already proved. Let me remind them. So properties of standard elements. Suppose we have two elements A, B in S. So two elements of the standard universe. Then what is the star of the unordered pair? Yeah. So it is a set of two elements, this unordered pair, and here let us take other combination, star A and star B. So this is the set of functions which take, say, f of I, such that B for almost all I. Yes, and we take this function f of I. It is the set of these functions equals the set of these functions. So this is the set. It is a pair. Yes. So it is a pair. It is a pair of what is this? It is the following. It is the set of G of I such that G of I depending on A and B are sets or they are individuals, it can be written different. Say if they are sets, G of I elements of A for almost everywhere, and the set of H such that H of I element of B almost everywhere. Yes? So important that this is a pair of two functions. Yeah, a pair of two sets. So this is one set, this is other set, and we form a pair of them, unordered pair. Yes, please.
What if A is not a set? What if A is like an element?
If it is not a set, then this is just A almost everywhere, and this is just B almost everywhere. If they are individuals, this.
In fact, shouldn't we have like MG or something like that? Here.
Yeah.
Like instead of G, should it be like the class, the equivalence class of all? Like shouldn't star A be composed of equivalence classes of such functions?
Yes.
Instead of just like the functions themselves?
Yeah. Maybe it doesn't change. Doesn't make much difference in this case. We will see. So here we have a dramatic thing. This is a set of functions. This is a pair of sets. Yeah? But if no, I assume for yes, assume that A and B are different. Then for any I, either Fi is A or f of I is B. So the index set I can be divided in two sets, where f equal A and where Fi is B. One of these sets has measure 0, and other has measure 1. And depending on what is measure 1, you have that this is f of I is A almost everywhere, or f of I is B almost everywhere. Yeah? So here, in fact, we have here just two elements, or we have many elements, but they fall in two groups. In each group, they all are equal to one another. So as a set, it has two elements. One element is Fi equal A almost everywhere, and or Fi is B almost everywhere. It is here. here yes, and just a minute. If f of I is A almost everywhere, yes, then it is this makes sense. This is a set of G such that for almost all I, G of I belongs to f of I, because if A is a set, then this AAA, it is just standard element, and the standard element is defined like this. It is a set. Yeah? So this means that here we have just two sets. What is here? One set is the set of sequences where you have G equals element of F of G of I elements of A, and the other set where each G of I elements of B. Yes, by this definition. Yes, and this is written exactly here. Yeah. So what is star A? Star A is what is written here, the set of functions, and the same star B. So I even don't need this. In this case, this is clear. Now I can repeat with some obvious changes to prove the next identities. That what is A, B star of A, B. It is no wonder that, so what is this? It is star of the following. It is A, and it is AB. Yes? Now, repeating this, what I told before, twice, so we have to first disclose what is this, and turns out that this is the set of sequences where we have what a star of the. No, okay. So after this, a little tedious reasoning, which again uses only the fact, after all, that no, the general fact is the following: that if the index set I is divided into a finite number of subsets, then just one of them has measure 1 and the other has measure 0. Yes, and so no wonder that it is the pair of star A, star B. No, we can write it is star A, and this is star A, star B. No, I have little time to explain it all, but it is approximately the same reasoning. And the third thing, that consider the element A restricted to B. No, in this case, A makes sense as a relation, B is element in its domain, and what is star in this? And again, no wonder it is star A restrict to star B. So, you know what? Let me present it as additional material. I will write and send you this part. It is important, but for now, please take it for granted, and then I will give you the proof, because it is pity to spend time in the lecture. So we have this thing, and now we can go further and consider, say, the case when A and B are sets. Suppose that A and B are sets, so they are as check minus as 0. They are sets. And what is star of A union B? A union B. So union is a new operation, but this operation can be, say, reduced to the previous schemes, to what was written there. Namely, we have a relation. I wrote union of A, B, C. The set of triple A, B, C, such that C equal A union B. Yeah. As any operation, it can be reduced to relation, or written as relation. Yes, and then A union B is nothing more than union reduced to the part AB. Yeah. So AB, let me write it so that C has is separate. AB and C. No, first, this is definition of a triple. Triples defined as a repeated pair on one hand. And so here the first argument is this pair. So if you take what is union restricted to AB, it is a C such that A, B, C in union, the unique C. And here this relation union is defined so that it really, this really holds when A and B are sets and you substitute them here, then the result will be the union. Yes? And now if you apply this rule, this formula, what is the star of say, here A restricted to B, here instead of A is union and B is this pair AB. Yes? So we have that A union B star equals union star restricted on A, B star. Yes? And this is what is union star. Union is a constant. Yes? Union is some relation in between three sets, which does not depend on sets. Yeah? So union star is we consider sequence of these constant sets, union, and then we consider all the functions such that for almost all I, they are in the union. For any I, we consider function, say A of I, B of I, C of I. For almost I, they are there. And then you see that this happens for almost all I. We have that if you take a function, this function, then for almost all I, it will be either in the set A or in the set B, or in the set on both of them. Yes? So if no, we can consider the case either it is in A and not in B, or it is in B, or maybe together A and B. Yes, so we have three cases. Only for any sequence, only one case holds almost everywhere, and so we, in short, conclude that it is A star union B star, because for any sequence, either for almost all elements it will be in A, for almost all I it will be in A, or for almost I it will be in B. No, or it can happen that both happens if A and B have good non-empty intersection. Yes, so we have this equality. Yes, and similarly, we have that star of A intersection with B equals star of A intersection with star of B. And star of A minus B is star A minus star B. All these equalities are proved by in the same line. So we introduce here the relation intersection. Yes, intersection. So A, B, C in intersection. Intersection is a subset of say Sn times Sn times Sn for some n. Yes, ABC is intersection if C equals A intersection with B. Yes, and now we construct here intersection star, and then we can describe what is the left hand side and understand that it coincides with the right hand side. And now I approach the transfer principle. No. In fact, it is a particular case of more general theorem. No, it is almost coincide. So let me call it Lohr's theorem. Lohr was a Polish mathematician or logician who proved this theorem. Yes, please.
Real quick, the intersection here, is it an intersection or an intersection? I'm really not sure if it is an intersection as it says in the Nonstandard universe, or the star of the intersection.
This is star of E is a set. Yes, is a set of I always each to say trajectories. Say a function of I, let me call them trajectories. So it is the set of trajectories such that for almost all I, they are in the set A. Similarly, set star B. So they have two sets, and this is intersection, their intersection is a set. Here we have simply sets A and B, and their intersection in the usual sense. So it is also a set, and so its star gives you some set of trajectories, and the sense that here we have two sets of trajectories and consider their intersection. Here we have also some set of trajectories. Yes, and the statement is that almost all trajectories of this set for almost all I are here.
So if I get what is going on is that if we take the intersection as a relation and we take its star, it's gonna be the same as the inherent intersection relation in the, like if we take
yes.
So that would be a proof of it.
Yes. And this is because of relation which I wrote of this place earlier. Yes. So these more apparently more general relation are reduced to the previous sort of relations, namely relations sort of object. It's not. It is maybe called set theoretical operation, but in fact it is specifically a restriction of some relation on some argument. In fact, the relation in this case is a function. Yes. So let me formulate this great theorem. Suppose we have a formula alpha alpha is a formula in the language L containing some constant say A, B, C, and so on, as many as we need, and no free parameters. All variables are bound by quantifier. Yeah. So it is how theorem looks. Any theorem looks like such a thing. If it has some variables, then it is always bound by quantifier for all, or there exist. Yeah, so in fact, we can consider this thing. Now we consider another formula. So let star alpha be a formula in the language star L of the universe star U. Be the same formula with all constants A, B, C, and so on, replaced by star A, star B, star C, and so on. Then the formula alpha is valid, it holds, yes, or is true, if and only if the formula star alpha is true in the system, in the universe star U. In U. In star U. Okay, so in principle we have all components to understand this. So every formula contains logical symbols which don't depend on mathematical universe. It contains constants which are individual names of all objects of our universe, and variables which also has no no say proper meaning, and they are just the names, just placeholders. So here we have a formula, yes, some statement which uses the symbols of our language, and where all the constants are elements of universe U, of standard universe. Now, among these constants may be some tricky things like relations, operations, and so on. So it can be something very involved. For example, a constant, we can find a constant describing, for example, a structure of some Lie group and its relation to its Lie algebra. It also can be regarded as a constant. Yeah, different Lie groups are different constants, for example, or something even trickier. But anyway, this is a constant. This means that it is a name of element of our universe. Now, having any constant in universe U, we can build a constant in a corresponding constant in universe U star, which is a standard element of U star. Standard. So I have shown how to do it. Yeah, and then we have, if you replace in this statement all constants A, B, C by the constant star A, star B, star C in the new in the universe star U, then we have a new formula, and the statement is that the formula in U holds if and only if it holds in U in star U. Yeah. No, it looks quite tricky in general terms, but let me consider example. Example, consider the following formula. Is the following formula. For all x in R, for all y in R, the following holds: x plus y equals y plus x. So this is a formula. So what is here? This is not a formula. No, I would say here we use a shortcut. This what is x plus y. So we have to write it in the form which where we can clearly see what is constants, what is variable. So let me introduce a relation. Plus of plus is a subset in R times R times R. Yes? So what is elements of plus? So the triple x, y, z is element of plus if and only if z equals x plus y. Yeah? And so here again, let me x, y, z like this. So that here is these first two variables are what we need. And now, what is x plus y? X plus y is simply this plus restricted on the pair xy. Yes? So we approach the standard form of notations for our language. And so our formula alpha is the following. In fact, alpha is the following. For all x in R, for all y in R, we have the following. Plus restricted on xy equals plus restricted on yx. And now we see clearly what are the constants. Of alpha. One constant is R. It is the set R. And the other constant is this plus. Plus is relation. Relation is a set. It is a subset of this set. Yes? So plus is a constant. It is a set which does not depend on anything. R and plus. Variables. It is x, y. Now let us look. These variables are preceded by quantifier for all. Yeah? No, in principle, if you go to the basis, you have to replace this for all that there does not exist such that this does not hold. But let me go without this. Yeah.
Here the R represents the does it, if I understand correctly, the R does not represent, like, it's not the object real numbers but the name of this object?
Yes.
Okay.
Yes. R is the name of the object, of course, and plus is the name. Because plus is some amount of the chalk dust attached to the blackboard. Yes, and the object is a set in R plus R plus R. So it is, I would say it is a plane. Yes. Variables. They are bound. By this. Because you see, yes, this means that nothing depends on them. You can write instead of x and y, z and u, for example. And the result will be, the mean will be the same. Yeah, so now we can write what is alpha star or star alpha is the following. For all x in R star, for all y in star R, plus should be replaced by star plus. Star plus restricted to x, y equals star plus restricted to yx. No, it is equal. Yeah. So we have this formula. Yes? And now let us try to, so to say, open the brackets and see what does it mean. What does it mean? What does it mean? X element of star R. Let us, when we discuss such objects, we start to the left, first say start and then the name of the object. Yeah? So X belongs to star R. It means the following. X equal x of I, and x of I belongs to R almost everywhere, for almost all I. Y belongs to star R means that Y is Y of I belongs to R also almost everywhere. Now, what is star plus of restricted to xy? So, what is star plus? Star plus, by the definition, equal, say, f of I. What is f of I? For almost all I, so f of I belongs to R times R times R. Let me write f of I equals xi x of I, y of I, z of I. So belongs to R times R times R, and x of I plus y of I equal z of I almost everywhere. Yeah. So this is now what is star plus restricted to xy? Restricted to xy. It is already familiar object, restriction of some set, say A on B. Yeah? So this is the following thing. It is this plus restricted on x of I, y of I. Almost everywhere. Yeah? And what is plus restricted to xi, yi? It is x of I plus y of I. Yes? So, this, you see that this star plus on the left hand side equals simply x of I plus y of I almost everywhere. Yeah? Now, similarly, the right hand side star plus restricted on yx equals, after all, y of I plus x of I also almost everywhere. No, we know that they are equal almost everywhere. Yeah. So this means that this holds. So star plus restricted on xy equals star plus restricted on yx almost everywhere. Yes? This means that this star alpha is true. So let us write from simply alpha. If alpha is true in U, we have that star alpha is true in star U. Star alpha is true in star U. Now, in other direction, it is even simpler. Can I say even simpler, or simply simpler? Or let's call it star simpler. Yes, so let us go other way around. So if star alpha holds, then in particular, let me write it here. Star alpha, let me write star alpha, then in particular we can consider x in star R, but x instead is star z, z in R. Y equals star t, t in R. Yeah? Then you have x is the following thing. X of I, which is equal to z almost everywhere. Y is t of y is y of I, which is just t almost everywhere. Yes, and so the meaning of this symbol is the following. We consider for any for all the i's for all I we consider x y xi plus yi. Yes, so xi plus yi equals yi plus xi almost everywhere, simply because this is z, this is t. Let me write equal z plus t equal t plus z equal yi plus xi almost everywhere. Yeah. So this conclusion for standard x and y. So this x and y are standard. Is even easier. So this is the proof in this particular case for this particular statement. No, the general statement go by tedious induction, so we can take a long formula. This formula contains different logical signs, symbols, then we take induction by the number of these symbols. This simple case and then goes more complicated case, but the level of difficulty is approximately the same. So it is long but locally trivial. So this is the loss theory, which also is called the transfer principle. Moment. Yes. No. Consider now a couple of examples. One moment. My God. There's no time to do anything non-trivial. What is star of empty set? Yeah. Star of empty set. No, empty set. Say we can take any set A minus A. And this is star A. Star of this formula A is a constant. Take any constant like this, because for any set A minus A is empty set. So this is star A minus star A. There is also a set minus itself, which is empty set. Now, what is star of, say, finite set? A1, AN. No, first, let's consider star of A1. Star of the set which contains just one element. It is the set containing just the star of A1. No, what is this set containing just star of A1? No, it is this A1 is a constant. If you consider star A1, it is also the equivalence class of sequences such that each, almost every term of this sequence is A1. Yeah, and these sequences are constant sequence which is not a set. This sequence has only, this class has only one term, so it is not a set. It is, can be denoted by A1 simply. Because we identify individuals and their standard elements of U, star U, which is this individual. And then we define a star of, say, A1, A2 equals star A1, star A2, Yes, and again, if you agree that these individuals is common, these also are individuals both in U and in U star. So if you agree to identify these individuals in U and individuals U star, say 0 is element of U, element of R, and at the same time element of U. And we agree that the corresponding element in star U is also 0. So then it is the matter of notation. It is a pair A1, A2, and so on. No, it is not so interesting. But what is next? Interesting next is not in fact proof that there exist some elements in star U which is not in U. We have to prove it. Now let us consider not the set R, which is more complicated. Consider the set N. Yeah? What is star N? So by definition, elements of star N are equivalence classes of function. So A in star N, if A is AI in N, and I in I. Now, what sort of I should we take? We always take it infinite, because otherwise it's all trivial. So let us take I equals N itself. Now it is the minimal infinite set which we can take. Then A equals the function A of I, such as I in N. Yeah? So A is a function. It's the name of this function of N with integer values. And we say that A less than B if, say, A, B in, no, it is B, are in the relation less, yes? So there is some relation, some subset in the subset in, say, N subset in N times N again. Yeah. So A, B in the relation of A. If so A and B in R. First we consider standard numbers. Now consider the numbers non-standard. Say U less than V if for almost all I. Yeah? And in this sense, I would say if you take every two non-standard numbers, non-standard integers, if u be in star n, then u less, in this case, star less than v, or u equal v, or u star more than v, in sense that this or this or this holds almost everywhere. Why? Because this index set I in this case, the set of natural numbers, is divided into three sets. One set where u of I less than v of I, other set where u of I equal v of I, and the third u of I more than v of I. Yes, one of these sets always has measure 1 and two other measure 0. Yes? So, in this sense, any two numbers, any two these non-standard integers are comparable. It's already a fine property of them. And now, let us consider the following number. First of all, we have standard numbers. Say A star in N star, A of I equals A. Almost everywhere, for almost all I. So these are standard numbers, how they are embedded into non-standard integers. And consider the number define u in star n, u of I equals I. Yeah? Because this I takes values in n, so we can do this. Then, for any A in n, u greater than star A. Yeah. No, why? Because u is growing sequence and star A is constant sequence, no, up to a set of measure 0. Yeah? And so the growing sequence will overcome the constant sequence somewhere. So after some finite number of steps, this sequence is more than this sequence. Yes? And any finite set is of measure 0. Yeah? So this means that this element u is more greater than any finite number. No, finite number which is transplanted to non-standard universe where it has all the same properties of finite numbers. And we constructed the first time infinite element, infinite integer number. Yeah. So, okay, so next time we will study some interesting properties of these integer numbers where the transfer principle plays a great role. So for today, our time is over.